All right, let's take this one step further and use free energy to predict the equilibrium position. All right, and the last thing I asked you guys to do was to predict delta G under non-standard conditions. And the way that we did that is by finding the delta G under standard conditions and then modifying those conditions, perhaps with, temperature, or perhaps with changing the ratio of standard conditions for pressure, for example. Well, here's what we know. A reaction like this, when we change the conditions, is going to change its spontaneity. And maybe the conditions will increase the spontaneity or decrease. But what we know is that a situation like this is not at equilibrium. How do we know? Well, if we're calculating delta G, it means the reaction has a direction to run. It means it's going to form products, it's going to form reactants. That's the definition of not being equilibrium. When is a reaction at equilibrium? When Q is equal to K. So we could plug K into this equation for Q, but that would be equilibrium. And what do we know about equilibrium? When the reaction is at equilibrium, it's no longer spontaneous. It's kind of in the middle. Well, what is delta G when we're in the middle? 0. So what we have when we plug K into this is 0 equals delta G under standard conditions plus RT times the natural log of K. Well, what this gives us is negative RT times the natural log of K equals delta G under standard conditions. So how do we solve for K? So let's back up a bit. We know that the natural log of K would be equal to delta G under standard conditions over negative RT. Now let's remember that R is always going to be 8.314 joules over Kelvin mole. If we could get this, all we'd have to do is do the reverse function of natural log. That's this guy on our calculator, this e to the x. And that would tell us our value of K. That would tell us the size. And we know that if K is greater than 1, it's obviously a situation where the products are much greater than the reactants. All right, so we can find the equilibrium position. We can find where the situation is going to end up. So let's try one of these. All right, let's try one of these out. And what we're going to try to find out is what is the value for K. We know natural log of K is going to be equal to delta G under standard conditions over R times T, where T is temperature in kelvins, and we have it right here, 25 degrees Celsius. So since we're looking for delta G under standard conditions, let's use our delta H and our S. So I'm going to find the overall delta H of the reaction, simply by using the sum of the delta H of the products. That is minus the sum of the delta H of the reactants. And that's pretty straightforward. Here's our products, here's our reactants, and so we're going to have 2 times negative 826. And what's nice is that the reactants are all 0. So that's pretty straightforward, and I don't have a brain today, so I'm just going to multiply this. Is negative 1652. There's our delta H. Do the same thing with our delta S. This one's a little bit more involved. We're going to have 2 times 90. That shouldn't be a plus, it should be a minus. Minus 3 times 205 plus 4 times 27. So let me do this, and through the magic of technology, I will get the answer for delta S instantaneously. Negative 543. Now let's be careful, because delta H is in kilojoules and delta S is in joules. So let's write our delta H in joules as well. 1,652,000. These are both in joules per mole, and this is joules per Kelvin mole. All right. Okay, so now let's plug this into our equation for delta G. It's equal to delta H minus T delta S. We've got a delta H of negative 1,652,000. Our temperature, 25 degrees Celsius, and we'll turn that into kelvins, 298 times our delta S, negative 543 joules over Kelvin mole. So we know that kelvins cancel. All right, so plug this into our calculator, and we get negative 1,652,000 minus 298 times negative 543. And we get negative 1,490,186 joules per mole, which means very spontaneous. What that means is that this reaction is going to run towards the products. It means it's going to run this way. It's very spontaneous. So what we want to do is find this value for K. We know it's going to run towards the products. So let's plug this in and see if we can figure out what our equilibrium position is. So we're going to say natural log of K is equal to delta G under standard conditions divided by negative RT. We just found delta G. Negative 1,490,186 joules per mole over negative R, which is 8.314 joules over Kelvin moles, times the temperature, which is 298 kelvins. What's cool about this is that all the units cancel. So what we get here is natural log of K is going to be equal to, I'm going to get my answer through the magic of technology. So we get natural log of K is equal to 601. Let's take the anti-log of that answer, and we get, look at this, isn't this interesting? We're going to take the reverse of natural log e to the x. Let's turn this on. Look what happens. Take the natural log reverse of 601, and look what we get. Let's see if this one will do it. Mine doesn't. It says, interesting, this one just shuts off. When I do it with my calculator, I get a screen that says calculation exceeds the range of values for this machine to explain, or to express. So that means K is enormous. We could say then that equilibrium is infinite. This reaction runs all the way. So try that one and take it for a spin.